All right. So, good morning. Welcome to the EBS deep dive session here at Thursday at reInvent. By way of introductions, my name is Ashish Palekar. I am on the product management team with Elastic Block Store, which means that part of my job and responsibility is listening to feedback from you, understanding why we build the things we build, and then making sure that we listen to our customers and do the right sets of things. And with me is?
I'm Mark Olson. I'm an engineer on EBS. I've been around EBS for a little over 7 years, and I get to build all the things that you guys come up with. So I get to have a lot of fun.
All right. So with that, we have a ton of stuff to cover, and this session is interesting in a couple of ways because we try to cover some basics, as well as then go through a deeper understanding of what some of the best practices and learnings that we've had from our customers. Just by show of hands, how many of you are relatively new to EBS? Just do a show of hands. A bunch of you. Okay. So the way this is going to be structured is I'll walk through some of the basics, and then Mark here is going to walk through some of the best practices and things. So there's a wide array of things that we'll expect to cover today, and so I'll try to go at a quick clip. Post the session, Mark and I will hang around here. Do stop by. Do ask us questions. Love to hear from you guys. All right. With that, where does EBS fit in? So if you think about the AWS storage portfolio, we have offerings in block, in file, and in object. Around those, you have capabilities around data movement, as well as around security and management. From a focus perspective, Elastic Block Store, EBS, focuses on the block storage portion of it, and that's what we're going to dive into today. When you think about block storage offerings within the AWS context, really there's two categories. One is our instance storage family. And within the instance storage family, you have SSD-based options, as well as HDD-based options. And then on the EBS side, you have SSD-backed options, as well as HDD-backed options. The SSD-backed options are our general purpose, or GP2 volume type, and our provision IOPS, or IO1 volume type. And our HDD-backed ones are Throughput optimized, or ST1, and cold HDD, or SC1. Again, we'll go into what those are and when it's appropriate to use them in a little while. So let's start with what is EC2 Instance Store. When you think about the instance store, really think about it as being local to the instance. It is non-persistent in the sense that if you start and stop your instance, the storage goes away. A point of confusion and question that we are often asked is, oh, what happens if you reboot the instance? And if you reboot the instance, the storage still stays, right? So the non-persistence really refers to when you stop an instance, what happens to that? But the important criteria here is that the life cycle of instance storage corresponds to the life cycle of the instance. So the data on the instance store is not replicated by default. What that means is you can put applications on top that can do the replication for you. Nor do you get capabilities like Snapshot, but you can create backup capabilities on your own. And again, it has SSD as well as HDD options within the product family. Okay? With that, what then is EBS? So if you think of EBS, think of it as block storage, but as a service. The key thing there is the life cycle of the storage is separate from the life cycle of the instance. And so the service is accessed over the network. You can create, you can attach, you can detach, and you can delete volumes. Right? A point of confusion often is it a disk? And really the answer is it's not. And part of that, part of the way to think about EBS is really think about it as storage that's distributed over a number of physical machines. And that's what allows us to give EBS the availability and durability characteristics that Mark will go into. So I mentioned earlier that the life cycle of the EBS volume is separate from that of an EC2 instance. What that means is if you start and stop an instance, the storage can still persist. That has some nice properties. What that means is if you change your mind and your workload changes, you can change the instance type that's attached to your EBS volume. You can take instance types up, you can take instance types down. And the way you do that is by detaching the EBS volume and reattaching it to another instance within the same instance store. The same is true if your instance fails. If an instance fails, you can simply spin up another instance, or later Mark will go into what we do with auto recovery and attach it to the same EBS volume. Key thing to remember, a single EBS, a given EBS volume can attach to a single EC2 instance. However, you can have multiple volumes that can attach to a single instance. Our recommendation is to split your boot volumes from your data volumes, because that gives you some nice properties about how you use those boot and data volumes for other capabilities. Okay. With that, let's dive into the EBS volume types. As I mentioned earlier, there's really two types, or two families, if you will, of volume types. There's the SSD-backed ones and the HDD-backed volume types. Within the SSD family, you have GP2 and IO1, general purpose and provision IOPS, respectively. And then you have your throughput optimized and your cold HDD, ST1 and SC1, respectively, on the HDD side. The key thing to remember is the SSD type volume types align with the properties of what solid-state devices provide you. So they can be random access devices, and so that lends itself to certain types of workloads. The HDD ones, on the other hand, tend to lend themselves to throughput-oriented workloads, and again, that is something that they are designed and work for. But between that entire family, you can cover a wide swath of workloads, going from relational databases, think MySQL, think SQL Server, SAP, Oracle, NoSQL databases, think Mongo, Cassandra, CouchDB, big data analytics workloads, Kafka, Splunk, Hadoop, data warehousing, all the way up to streaming media workloads like transcoding, encoding, rendering, file system services. Right? So again, there is a wide spread of workloads that you can deploy given the volume types that we just described. The very logical question from there that follows is, okay, how do I choose my volume? And really, it starts with a two-pronged question. What is more important to your workload? Is it IOPS or is it throughput? Okay, so let's say IOPS is more important to your workload. And in that case, then the question you have to ask yourself is, do I need IOPS that is greater than 80,000 or less than or equal to 80,000? So why 80,000? Every EC2 instance connects to EBS, and we refer to it as the EBS has a specific amount of bandwidth and throughput and IOPS associated. The maximum that an EC2 instance can do, we call it EBS-optimized IOPS, is up to 80,000. And so what that means is that is the max that a single EC2 instance can do across all the EBS volumes attached to it. And in that case, if it is more than 80,000, you should use an SSD-based instance storage family. If it is less than 80,000, the question there is, what latency profile is your application okay with? Is it okay with a single-digit millisecond latency profile, or does it need a less than 1 millisecond latency profile? If it's less than 1, again, the answer is an SSD-backed instance storage family. If the application is okay with single-digit millisecond latencies, Then you have to gauge between cost and performance. The answer is cost. The volume type is GP2. So what does GP2 look like? In case you missed it, we announced this on Monday, but prior to Monday, the baseline for volumes was going from 100 IOPS up to 10,000 IOPS, increasing at 3 IOPS per GB. Post-Monday, what we announced was you now get up to 16,000 IOPS, right? So you get 60% more IOPS per EBS volume that you have. And your throughput goes from 160 megabytes per second to 250 megabytes per second. Again, this is the core volume type that is great for boot volumes, low latency applications, and bursty databases. Going back to the questionnaire, what if performance is more important? In that case, your answer is likely IO1, or a provision IOPS volume type. So what does that look like? Up until Monday, we supported up to a maximum of 32,000 IOPS and a throughput of up to 500 megabytes per second. The way it used to scale was really a 50-to-1 IOPS to GB ratio, so that a volume of 640 gig could get up to the full max of 32,000 IOPS. The nice thing is, on Monday, what we launched was doubling of that maximum, right? So now you can go from 32,000 IOPS up to 64,000 IOPS and up to 1,000 megabytes per second in throughput. Now, to get the full performance of our provision IOPS volumes, you will need a Nitro instance, Nitro-based EC2 instance, which is our C5, M5 family and beyond. But that now allows you to go even higher in terms of performance for your workloads. And so that performance chart I just showed you now starts to look like this, which is you can go all the way up to 1,280 gigabytes with the same IO to GB ratio of 50-to-1 and hit the maximum of 64,000 IOPS. And very excited about bringing this to our customers. And so that's what the profile looks like, with a baseline of 100 IOPS going all the way up to 64,000 IOPS, with a throughput going all the way up to 1,000 megabytes per second, capacity ranging from 4 gig to 16 terabyte. If your application needs critical sustained IOPS, then likely provision IOPS is the right offering for your workloads. Okay, let's flip over to the throughput side of the house. What if your workload is throughput intensive? It's going to look very similar. The question you have to ask yourself is it small random IO-based throughput, or is it large sequential IO? If it's small random, that will, again, bias you more towards the SSD side of the house. If it's large sequential, then the next question is, well, is it more or less than 1750 megabytes per second? Why that number? Because that's the maximum amount of throughput from a single EC2 instance to the set of EBS volumes connected to it. So if it is greater than 1750, then that biases you towards our D2 sets of instance family. On the other hand, you need less than 1750 megabytes per second, then you have to ask yourself the question, what do you care about more, cost or performance? If it's performance, then the answer is our throughput optimized family, ST1. Let's go into that. So ST1, or our throughput optimized HDD family, starts with a baseline of 40 megabytes per second per terabyte, going all the way up to 500 megabytes per second, again, with a burst going from 250 megabytes per second per terabyte up to 500 megabytes per second. The key thing to remember is that the minimum starting size for the ST1 volume type is 500 gig, going all the way up to 16 terabytes. The other key difference you'll notice from the SSD families, which were IOPS-based choices, really here, what you're choosing is throughput based on the capacity that you have. If you have workloads that are large block, sequential, needing high throughput, then that's what SD1 is going to be useful for. Okay, what if cost is more important? Then the answer is cold HDD or SC1, right? So what does cold HDD look like? Cold HDD starts with a baseline of 12 megabytes per second per terabyte, going all the way up to 192 megabytes per second, with a burst going from 80 to 250 megabytes per second. Again, the entry capacity is 500 GB, going all the way up to 16 terabytes. This one is, again, throughput intensive, but not as throughput intensive as SD1, and therefore think of use cases like logging or as a secondary copy of your data. That would be a more appropriate workload for SC1. So that's the taxonomy, going all the way from instance storage to our SSD-backed EBS storage types, to our HDD-backed EBS storage types, to instance store that is disk-based. What if you don't know your workload? What if that is something you don't know the profile and how that fits? Our recommendation is start with GP2, right? And the nice thing is we have a capability that I'll go into a bit called elastic volumes. You can start there, observe your workload, and then adjust accordingly. And that gives you a good branch-off point into our other volume types. By the way, you can mix and match these volume types within your infrastructure and take advantage, because these are different cost points and different cost profiles. An example of this is with Zendesk, and they had an Elk stack, that was using the i2 instance family. After moving over to EBS and using GP2 in addition to our streaming volume type, that resulted in them saving over 60% in terms of the overall cost of the solution. So pretty exciting to see how customers mix and match our volume types in order to get cost savings for their workloads. Just so you have a sense of the cost points, these are our cost points. So GP2 is 10 cents per gig. Provision IOPS is 12.5 cents a gig and 6.5 cents per provision IO. SD1 is 4.5 cents per gig. SC1 is 2.5 cents per gig. Capability that Mark will go into a little bit is Snapshot, which is essentially our equivalent of how to take a backup, is 5 cents per gig month. So I touched on elastic volume. What if you start on GP2 and you decide to change your volume types? And that's really what our elastic volumes capability is about. It allows you to increase your volume size, allows you to change your volume type, and allows you to increase or decrease your provision IOPS, completely non-disruptively to your application. Why is this important? Let's say you're running an application with a database on an EBS volume, and you decide you are running short of IOPS. Well, with elastic volumes, you can increase the amount of IOPS allocated to your EBS volume and thereby get that improved performance. So how do we modify? We recommend 4 steps. Snapshot your volume in case things go wrong, modify your volume, monitor your modification, and then extend your file system. I'll cover each of those 4. So snapshot volume, pretty standard. Use the create snapshot, use the console, use the CLI. That'll allow you to create your snapshot. Your next step is modifying your volume. In this case, we're going from a GP2 volume type to an IO1 volume type, right? And one of the questions that customers do ask is, do I have to make one change at a time? And the answer is no. You can actually change multiple things. In this particular use case, we are changing the type, we are changing the allocated IOPS, as well as we're changing the size, right? So you can combine different changes within one modify volumes command. What you then do is monitor your volumes. And the way you monitor, in this case, is with the describe volumes modification command. Two things that you look at is what's the modification state. In this case, it's optimizing. And that gives you the overall progress relative to where you are from an elastic volume standpoint. The UI, similar thing. You can go look at your in-use. It's modifying, it's optimizing, and then it's done. The last phase of this is now for your file system to recognize that additional capacity. And so in this case, you would go list through the file system. We've chosen XFS as an example. And in this case, you then either use resize to FS or grow FS to take advantage of the new capacity. On Windows, you go into Disk Manager. And in Disk Manager, you go extend the volume. You'll see the operating system will see the new capacity. You'll go extend that volume, right? And then take advantage of that additional space. And that allows you to, you can also use PowerShell commands, by the way, to resize your disks. So some tips and tricks. And I'll cover one that has come up recently in customer conversations. First is your modification must fit within the volume specs. Right? As I mentioned earlier, SD1 has a minimum entry size of 500 gig. So if you're converting from a 1 gig GP2 volume, you can't convert to a 1 gig SD1 volume. You need a minimum of 500 gig assigned there. You can modify volumes once every 6 hours. Current generation, you do not need a stop, in instances, you do not need a stop start or an attach. And if you have volumes that were created prior to November 2016, those may require a stop start or an attach. One last thing that does come up is some customers do ask us about what kind of performance I get. The general guidance is you'll get the least common denominator, at least, of the performance of the two volumes while it is in the state of modification. Right? So let's say you're migrating from a GP2 to an IO1, and let's say the GP2 in this case was the lower performance volume. You would at least get that performance as you're migrating that volume from GP2 to IO1. Right? So that's why it will be non-destructive to your application. Doesn't stop there. We've seen customers who've looked at it and said, I can now start to automate with elastic volumes. Right? Combine that with CloudWatch alarms, events, and Lambda to start doing things in a more automated fashion. So what are examples of this? Well, you can right size in an automated way. You can publish a free space metric to CloudWatch, use Lambda to extend the volume, resize the file system, and take advantage of that new capacity. You can run a CloudWatch alarm to monitor what your IOPS consumption is on your volume and decide if you're running out of IOs and if you need to extend the volume. Right? You can then automatically initiate a workflow where you need additional IOPS for the volume. With that, Mark?
Thank you. Now the fun part. So how many of this was this review for? Or how many people was this review for? Show of hands. Most of you, that's great. So what I'm going to go through is a few things on how to use EBS, some tips and tricks here. So in order to use EBS, what do we need to do? We need to attach it to an instance. And so this is pretty straightforward. We've got an API, attach volume. You can do it through the CLI or console. Provide an instance ID, your volume ID, and a mount point. And now this mount point is how it's going to show up in your instance on our Xen-based instances. And so when we attach it to a Xen instance, do an ls block, we can see that. XVDF is the volume that I just attached. It's a nice, giant 1 gigabyte volume. Probably wasn't just doing anything other than this demo, because you can't do a whole lot with 1 gigabyte these days, can you? How many people have launched Nitro instances? A few of you. Of those that just raised their hands, how many are confused by how EBS volumes appear in Nitro instances? So when we built Nitro, and we went through the story last year, but I'll give you kind of an overview. We moved all of the device emulation onto our own custom hardware called the Nitro card. one of the things that allowed us to do was give more resources in the virtual machine back to your instance. On that card, we actually look like a PCI device to your instance. And so since we've got a PCI device, we decided, well, most operating systems these days have support for NVMe. NVMe is a pretty good programming model. It's pretty easy for us to do. It's pretty easy to iterate in the driver community. And so we decided to expose as an NVMe device. Now, the downside here is in Linux, for example, we have to rely on how that PCI bus is enumerated in order to give you your actual volume ID. And so Linux gives you these NVMe prefixed names depending on how the order that the EBS volume is actually attached and enumerated. And now this can change across reboots. It can change across stop-starts. If something's slow, if you do attaches, detaches, attaches, and then you reboot, you might end up with a different order. So I don't recommend relying on these NVMe 0 and 1 names. One of the things NVMe did give us the opportunity to do was add some more detailed information that we really had a hard time doing with Xen. And so we populate, as part of the NVMe information, the serial number is your volume ID. We had to take out the dash because NVMe only gives us 20 characters. But you've got the volume ID there. The model name is EBS, or Amazon Elastic Block Store. This is to differentiate it from our instance store, our new instance storage volumes, which are also NVMe. And those will show up as Amazon EC2 instance storage. Now, that mount point, we still try to carry through for you to give you some way to identify this volume in a programmatic fashion. And so NVMe gives us the ability to add vendor-specific data. We took the first 32 bytes of that and put that mount point that you specify into that data. And so you can use the NVMe CLI to actually get that data, and there are a few other ways that you can do that too. Now, if you're using Amazon Linux, we made it even easier. We wrote a little Python script that parses out the volume ID, gives you back the one with the dash that you would expect, so that if you've got scripts that rely on that volume ID, you can use that. And that block device mapping comes out of there as well. In addition, we created rules for the UDEV system so that when your volume is attached, the NVMe 1N1 gets created, and then an event notification is sent to UDEV. We poll for that, or we look at the device for the mount point, and actually create a symbolic link to that NVMe 1N1. And so you can still reference it with these UDEV rules using the XVDF that you specified on the console. Now, you can also, when you create the file system on there, specify a label, which is something that will stick with the EBS volume for its life. So you can always reference it by that. And Linux, by default, has UDEV rules that will create symbolic links to that label as well. So I highly recommend that you use one of these more stable methods to identify your block devices and your EBS volumes. All right, some more best practices. We're going to start out with security. Security is one of the most important things. How many people have used EBS encrypted volumes? Cool. I like to ask this question every year, and I like to see that more and more hands are getting raised. So we've got EBS encryption where you can just do a checkbox to encrypt your EBS volume. It uses your default key. So there's no extra management, no maintenance overhead. We'll take care of all the encryption. Now, one of the benefits of our Nitro cards is that this is all offloaded into hardware, so there's no performance penalty for doing encrypted volumes. So all you do is check the box, create the volume, you're good to go. Now, the one thing the default key doesn't give you is it doesn't give you the ability to do finer-grained access controls and a few other things. So if these things are important to you, we recommend that you create a custom KMS master key. And so you can create this key, allows you to do a key rotation policy that could be different from ours, cloud trail auditing, and then the access controls that I talked about. And then when you select the encrypted volume, you just change the key that you're going to use. So instead of using that default key, you use this new EBS master key that I just created. Now, for those of you that are using encrypted volumes, do you do a lot of snapshot sharing and things like that? So one of the things that we've had to do is you can share encrypted volumes, but you have to actually create a snapshot. and then copy that over into the new account in order to create a new image for it. So in preview, what we're coming out with soon is the ability to do one click so that you can take an EBS volume that is either unencrypted AMI or encrypted with a custom CMK that's shared, and just do one click, create an instance from it. So you don't need to do that copy image anymore, and you don't need to take that time. Excuse me, just a second. 4 days in Vegas really dries you out. All right, so because EBS volumes persist beyond the life of the EC2 instance, we really need to think about the reliability of EBS separate from your EC2 instance. And so we think about volume reliability in two ways. The first is availability. And we define availability as the ability to access your data. And so this accounts for our software, the network in between your instance and the EBS storage servers, and the uptime of our service. And so from this aspect, we're designed for 5 nines of availability. And we track this continuously. We've got aggressive alarms and constantly monitor this so that we know that we're even getting close. And our alarms are set way above this 5 nines design point. Second is durability. And that's once we get to the storage server that's hosting your data, can we get it off the media? And so here, EBS is designed for an annual failure rate of 0.1 to 0.2%. So the way to think about this is if given a statistically significant sample of volumes, you can expect 1 to 2 volumes to fail out of 1,000 every year. Now, this is the design point, but you can reduce the probability of data loss when a volume fails by taking snapshots. And so EBS snapshots are a point-in-time backup that's crash consistent of the modified blocks of your volume. Now, these snapshots are stored in S3, which is a service with 11 nines of durability. Now, since it's only the modified blocks, we're able to do incremental snapshots, and so you only pay for the new data on a new snapshot. What this also means is that we'll keep track for the entire lifetime of that snapshot of what data is unique to that snapshot. So when you delete a snapshot, you don't have to worry about any future snapshots that rely upon that. You can just delete that snapshot, and we'll delete only the data that's unique to that snapshot. Now, when you take snapshots, we also recommend that you tag them. Tagging is an important feature that allows you to better manage your AWS resources, and in this case, snapshots and volumes as well. They give you the ability to assign a simple key-value pair so that you know what those snapshots are for, and it allows you to visualize, analyze, and manage those resources. Now, you can also take these tags and activate them for cost allocation tags, which I'll talk about in a minute. Earlier this year, we made it a little bit easier to create tags on your snapshot. So now you can create tags when you create your snapshot. You no longer have to wait for the snapshot ID and then add tags to them. So this allows you to actually keep track of those snapshots a lot more conveniently. And so you can do that with the CLI or the console as well. Now, I mentioned Cost Explorer. Cost Explorer is an interesting thing that we brought out last year. And what it allows you to do is you can assign tags that are cost allocation so that you can look at your storage usage and costs dedicated to specific tags. So maybe you want to track your dev, test versus prod workloads, and you can see how they compare and how your costs for those snapshots are. Now, I mentioned that EBS snapshots are crash consistent. Most applications can deal with that. It's like pulling the power plug out of your computer, and so there might be some log. The log will replay, and it'll fix itself. But if you need application-consistent snapshots, you can do that on Windows through EC2 SSM. And so we integrate with VSS now. So all you have to do is use the policy generator, create an IAM policy for AWS, allow describe instances, create tags, and create snapshot, and then attach that to your Windows instance. And this has been available since last fall. Earlier this year, we announced the ability to do finer-grained resource-level permissions on snapshots. And so you can use tags to limit the actions that specific IAM users can actually take. Now, one really interesting use case that I heard about a few days ago was taking snapshots, copying these across region, and then using resource level permissions to restrict the number of people that can delete that snapshot to the root account. So this is one way that they could do a disaster recovery that's separate from their existing account in their production environment. Back in July, so we've got all these primitives that allow you to take snapshots and tag snapshots and manage snapshots. But back in July, we announced Data Lifecycle Manager. And what this does is it allows you to create policies, again via tags, to enforce regular backup schedules, retain those backups. So if you want to have some sort of retention policy, either for compliance or for just disaster or recovery purposes, and then control those costs by deleting old snapshots. And then this is controllable through IAM users as well. And no additional cost. All right, so what can we do with a snapshot? EBS volumes are zonal. And what we mean by that is that your EBS volume lives entirely within an EC2 availability zone. They can attach to instances within that availability zone. So what if you want to take your volume and put it in another availability zone? You can use a snapshot to bootstrap your application. So you create a snapshot, you can launch another volume in the other availability zone, and then if your application has some sort of catch-up replication, things like that, you can just have that differential spot. The other thing that you can do is you can take a snapshot, you can copy it to a different AWS region. Perhaps this is, you want to go to US East and US West. Maybe you want to launch in one of our new regions that we're announcing. Maybe you just need a disaster recovery copy. And so you can copy to another region and then create volumes and availability zones in that region as well. All right, so what about EC2 instance failures? Since the lifecycle is separate from your EC2 instance, when the instance dies, if there's a failure of any sort, that EBS volume will stick around. So all you have to do is create a new EC2 instance and then attach that EBS volume to that EC2 instance. Now that'd be great, but again, that's a primitive. It's a lot of manual work. And so with an EBS-only EC2 instance, so if you don't have any instance storage attached to it, you can actually use EC2 instance recovery. And what this allows you to do is create a CloudWatch alarm that when that alarm triggers, we will actually replace your instance. Now when we replace the instance, the nice thing about us doing it is that it retains all of the metadata, so your IP, your volume attachments, the instance ID. So it just looks like the instance went through a reboot. Now if the underlying hardware failed, we'll put it onto a different server. Maybe we'll reboot it in place, but we'll look at the health of where your instance is and make a decision on where to move that instance to. And so like I mentioned, this is available on our newer instances, C3, which isn't really new anymore, but that's when we started launching it, if it's an EBS-only instance. A little bit of housekeeping. By default, boot volumes are set to delete when you terminate your instance, and data volumes are not. And so with delete on termination false, that means that when you actively terminate your instance, we'll detach that volume, and it'll just sit there. Maybe that's what you want. And if you want that, go ahead and tag that volume so you know what's on it, so that a year from now, you don't have to mount it and try and figure out what's on it and why you kept it around. But you can then attach it to any other instance. If that's not what you want, maybe it's a dev test workload, and so you don't really care about the data. You can set all of your data volumes to delete on terminate equals true. And then what happens when you call the terminate API and terminate that instance, we'll also delete that volume for you and clean up, saving you a little bit of cost. All right, performance. One of the first things I get asked when I'm talking to somebody about performance is, do I need to initialize my volume? You know, I found a blog post from 7 years ago that said you had to do a whole lot of things. If it's a brand new EBS volume, all you have to do is attach it, it's ready to go. You'll get full performance on it. If you create that volume from a snapshot, what we will do is we will load that data from S3 in the background. If you request an I/O, if you do a read I/O to a segment of that volume that we don't have yet, we will fetch that data from S3 at the head of the line, so in front of everything else that we're loading in the background. So it's just-in-time, on-demand loading there. Now, we've done some performance improvements over this, but if that's not good enough for you, what you can do is you can do what we call initialize, which is doing a random read across your volume. And I say random because that's how we load it. We're a distributed system, and you're going to take advantage of all of our back-end throughput to S3 that way. And so here's an example of FIO. Now, the fun part about this FIO command, when you create a volume from Snapshot, you attach it, you run this FIO command, FIO is going to report that it's going to take 3.5 days to load all your data. That's because it looks at the very first request at how long it took, and then extrapolates that out to the time. As we load more and more data, your volume is going to speed up. So you don't actually have to let this finish. We're going to load more data in the background than this will actually read. And usually when it gets to about 20%, you'll have to monitor your performance. But when it gets to about 20%, we've loaded enough data and that your volume is going to get full performance from that point on. So just keep an eye on that. You don't have to let it finish. Just when you get full performance, you can cancel this. All right, how do we count I/O? So for our GP2 and IO1 volumes, which are SSD-backed volumes designed for random workloads, we'll opportunistically merge those IOs into 256K chunks. And that's up to 500 megabytes a second. And then for ST1 and SC1, we'll merge into 1 megabyte chunks. Now, that's because those are hard drive products, really designed for throughput to take advantage of the mechanics of a spinning disk, where the seek time is really the expensive part there, but once we get that head parked, we can just read that data all day long. And so this helps you maximize the burst capability of your volume and potentially minimize the number of provisioned IOPS that you need to provision. So let's go through a few examples of what this looks like. So if you're doing 4 random IOs, each one 64K, we're going to take this train, load up the boxcars, 1 boxcar with each IO, and ship that off to EBS. And we'll count that as 4 IOs. So if you're doing sequential IO, so we'll take the first example as an SSD-backed product. Each IO is 64K. We'll park those into the same boxcar. And now the important thing to remember here is this is logical merging. We don't hang on to your I/O waiting for some deadline to approach or the next I/O to come in. We will actually just keep track of those I/Os for you and let the I/O go through. And if we notice that the next one is adjacent, then we won't take anything out of the bucket for it, and we'll send it along like it was part of the same I/O and kind of logically merge those together for you. And so this 256K I/O is going to be counted as 1 I/O. Similar thing with our streaming product. If we do these 64K IOs, it's the same sort of thing. And we'll just keep adding these on into the bucket until you get to the 1 meg, and then we'll close that bucket and go to the next one. Now, if it's a large I/O, it's kind of the flip side. We'll split those apart. So for a 1 meg I/O on our SSD-backed products, we'll split that apart into 4 segments. And so that'll actually count as 4 IOs on our SSD-backed products. Most workloads aren't purely random. They aren't purely sequential. They're kind of a mix. And so this is really where we need to think about how do I get the best benefit out of the volume type, and how do I best choose the volume type. So if this is an ST1, SC1 volume, and we're doing these larger sequential IOs mixed with smaller random IOs, we're going to merge them together as much as we can. But these 6 IOs are going to be counted as 4. So we merged it a little. It's not 6. But it'll count as 4 megabytes of burst, even though your application only got 1.5 megabytes of data. So there's a little bit of a loss there when you're doing some random I/O on our storage products, on our stream products. All right, so GP2, ST1, and SC1 all operate with a burst bucket model. And I'm going to go through a really quick explanation of how this works. I used to spend about 20 minutes on this with confusing charts and graphs and everything else. But I'm going to show you a little trick in just a few moments. And so all of our burst volumes operate on a token bucket model. And so for GP2, that bucket is sized at 5.4 million credits. And you're accumulating those credits at 3 IOPS per gigabyte per second. And you're allowed to spend those at 3,000 credits per second, or the 3-to-1 ratio if it's greater than than 3,000. So here's what it looks like on a graph. With our new 16,000 IOPS limit, if you have a 5.3 terabyte volume, you'll get the full 16,000 IOPS. All GP2 volumes have a minimum of 100 IOPS. So if we have a 300 gig volume, you're going to get a baseline of 900 IOPS, burst up to 3,000 IOPS. But the question is, how long does 5.4 million credits last? And so it's dependent upon your volume size because of that fill rate. And so our smallest volumes are designed to burst for 30 minutes. Right? And that's where that 5.4 million comes from. But as we increase in size, we can burst for a longer and longer period of time. So that 300 gigabyte volume, you can burst for 43 minutes. If you go up to 500 gig, it's an hour of burst. And then as you approach 1,000 gigabytes, you get a very long period of burst, so 10 hours. You get really close to almost infinity, and then you get above that into the non-burst regime. So here's the easy way to do it. We've now got a burst balance bucket, or a burst balance metric, rather. And so this is expressed in a percentage of your burst bucket so that you can figure out how much you're using. And so in this example, I used a benchmark. Benchmarks are great because they show you maximum performance. Benchmarks are terrible because they don't represent your workload. So I ran FIO for an hour on this 500 gigabyte GP2 volume. So I've got the 3,000 IOPS baseline, or 3,000 IOPS burst, and then 1,500 IOPS baseline. And so you can see for that 1 hour period, I'm getting, my burst bucket is depleting while I'm getting that 3,000 IOPS. And so that's the number of operations on the right-hand side of that graph over a 5-minute period, which is why it says 180,000. If we zoom out on the graph, after I stop my little test, you can see my burst bucket refilling. So we refill as much as we can, as quickly as we can when you're not doing that I/O. And so when you see spikes in your application, the down periods between those spikes will actually be filling your bucket back up. Now, it's important to remember that GP2 volumes are designed for most workloads, and we find that a small fraction of a percentage of volumes ever run out of their burst bucket. So most workloads will benefit from GP2. Our throughput volumes operate on a similar principle. The biggest differences here is that it's accumulating based on throughput, not based on IOPS, and your bucket is sized based on the size of your volume. And so that 12 megabytes per second that you see for SC1 is an interesting number. If you do the math, what that does is it allows you to do a full scan of your SC1 volume every single day. So you do 12 megabytes per second times 86,400 seconds, you get to about a terabyte. And so that's the design point of SC1. And ST1 gives you a little bit more, 3.5 times a day that you can do a full scan of your volume. And so here's what ST1 looks like on a graph, and you can see that at 8 terabytes, you get 320 megabytes per second base with that 500 megabytes per second burst. And right around 12 terabytes is where the burst and the base curves meet. SC1 is a little bit colder, again, designed for 1 scan a day instead of 3. And you'll notice that the base and burst never meet. So if you do need that 250 megabytes per second, you'll have to have some downtime in there, and that's part of the design point of the volume. So from a data transfer standpoint, I showed this in the way that we merge. But here's a comparison that if you're doing purely sequential versus purely random workloads on an ST1 volume. So we're doing a large 1 megabyte sequential reads here. If I let that run for 3 hours, I get almost 5.5 gigabytes of data off of that ST1 volume. But if I'm doing 16K random, I'm only going to get 87 gigabytes. Pretty big difference there, and that's part of the design point of the volume. So how do we know what our workload's actually doing? A lot of workloads you don't actually get the opportunity to choose, so you have to monitor. And so if you're on Linux, you can use IOStat. IOStat gives you the average request size. There's some averaging and rounding in here, so it's not going to quite make it all the way to one megabyte. But this example here, you see I've got 2046 sectors, and those are 512-byte sectors divided by 2. We get to about 1,024, probably doing a 1 meg workload. If we use perfmon, we can get a similar view of what our workload's doing. We can also use CloudWatch. In CloudWatch, what you'll see is 128K, and part of the reason for that is how we split it on the back end and how we report these. So this is pre-merge what we're going to see. This doesn't show you the post-merge. And so if you want to know and understand how you're merging, you can compare this to your burst balance. And if your burst balance isn't going down, we're probably merging for you. If you're seeing less than 64K or around that neighborhood, you're probably doing some random workloads in there, even though you think you're doing sequential. So here's a performance tuning tip. If you are doing large sequential reads on our streaming products, and only reads, and only large sequential, we recommend that you increase your read ahead. And so this is per volume configuration, not persistent across boots. The default for Linux is 128K, which means that every I/O, Linux is going to expand that to at least 128K. So if you want to take a look at it, this again is expressed in sectors. So here's a simple command to increase it to 1 meg. The caveat here is if you are doing small random I/O, it's going to degrade your performance even more. You submit that 4K I/O with a 1 meg read ahead, Linux is going to expand that all the way to a 1 meg I/O. And so you're going to have to wait for that to finish before some of the next I/Os. So if you're doing a lot of them, it might stack up. EBS-optimized gives us dedicated network bandwidth. And now this is enabled by default on all of our current generation instances, and that's all of our instance types that have the Nitro card, even if they're Xen or Nitro system, Nitro Hypervisor. And so we started using the Nitro card with our C4 family. And so this is enabled on all instance types. For our older instance types, you can enable it via stop-start. So you stop your instance, modify the attribute, and then start the instance. I highly recommend this. What it does is it separates out network throughput specific to EBS to give you more consistent, more understandable performance that your application won't conflict with. Now, it is important to select the right instance size. Every instance has a specified amount of EBS-optimized throughput associated with it. And so if we take a C4 large and attach a 2 terabyte GP2 volume, expecting to get 6,000 IOPS and 250 megabytes of throughput, the C4 large only has 62.5 megabytes per second of throughput, and which equates to about 4,000 IOPS. And so your volume is bigger than that EBS throughput allows. So you're not going to get that full performance. So what you'll want to do is you want to go to a bigger instance size. And so in this case, I'm doing an IOPS workload. So we'll go up to a C4 2x large, which will give us 8,000 IOPS. That same 6,000 IOPS volume, we'll be able to get the full performance out of it. Now, when we were building Nitro, our Nitro system instances, we gathered a whole lot of data on how customers were using EBS-optimized. And similar to GP2, ST1, SC1, we noticed that most workloads are spiky and don't really have sustained traffic. And so what we did is we enabled the ability to burst your EBS-optimized throughput on our smaller instance sizes. So on the example of C5 large, you have 30 minutes of burst. And what this does, it allows you to burst up to a larger instance size's amount of throughput for that 30 minutes. So with that bursty workload, you can probably accomplish it with a smaller instance size. And again, this is our burst bucket model where we're constantly refilling so that you will get that 30 minutes over the period of a day. Now, when do you want to RAID? I hear a lot of questions. What if you need more than 16 terabytes of storage, more than 1,000 megabytes of throughput now, more than 64,000 IOPS? That's when you want to RAID, and you want to do a RAID 0 here. One thing that I do recommend against is doing RAID for redundancy purposes. So EBS is already replicated through our distributed system. And if you use RAID 1 or RAID 5 or 6 or any sort of erasure coding, you're going to reduce the amount of EBS-optimized bandwidth available to your workload. All right, a little bit of CloudWatch helped us out earlier this year. They announced metric math. And so one of the things that we've been able to do with that is advise you can actually take a look at all the volumes that are attached to your instance, aggregate them together, and provide an instance view. And so here I did a 10-disk RAID, and I created 2 metrics to show me both IOPS and throughput across all those volumes in one simple graph. And so I can see that in this test that I was doing, I was able to get that full 1.76 gigabytes per second of throughput, which is the maximum that any EC2 instance can deliver to EBS. All right. So in summary, select the right volume for your workload. If you don't know, start with GP2. Use elastic volumes to change it. You can do that up to 4 times a day. Select the right instance for your workload. So make sure you've got the right size, the right compute ratio, the right memory ratio. Take snapshots, tag snapshots. Use our tools to automate that for you. And then use encryption, whether you need it or not. Thank you.